start today's lecture. I have 4 more examples to illustrate. We just, in addition to the one we demonstrated on Wednesday, in that example, we find the 2 eigenvalues. And for each eigenvalue, we find an eigenvector. And we show that we collect these 2 eigenvectors together, and then we show that they form a basis, okay, for the vector space V. Right? And so this becomes to an eigenbasis, so that relative to this new eigenbasis, the metric representation of the linear operator T becomes to be a diagonal. Okay? All right? And so this is the notation we used for the first example. And we will continue to use the same notation for the rest of 4 examples today. Okay? Now the second example. This time, right? So the F is R. So we can see the real case. Right? So the vector space is a real vector space. And the A is now to be 2, 1, 0, 2. Right? So the metric representation becomes to this one. Right? So in this case, the eigenvalues of T, right, are solutions of the following polynomial in lambda. Okay, so we will. So determinant T minus I, which is equal to the determinant of A minus lambda 2.2. So this is determinant of the matrix become 2. So this is lambda minus 2 square. All right, so we have to solve this polynomial equation. Any questions? Okay, so we have to solve them. And the solution, all right, so which is 2, 2. So we have a repeated solution to 2. All right, so T has only one eigenvalue, lambda equal to 2, with algebraic multiplicity 2. Right, so this is called the algebraic multiplicity, okay, 2. Now our purpose is to find a diagonal representation, right? So T has a diagonal metric representation. Right? So T has a diagonal metric representation relative to a basis, say C U W or V, right? This is our goal. If only if there exists a basis C for V such that Tu is equal to 2U and TV equal to 2v. Okay? So we have to find a basis, right, for the vector space V such that U and the W should be eigenvectors associated eigenvalue number equal to 2. Okay, so we should have this one because 2 is the only eigenvalue we have. So every eigenvector should be associated with eigenvalue 2. Okay. All right, so that there exists an eigenbasis. Right, so we have to find an eigenbasis C for V. Okay, so to find so T has a diagonal matrix representation relative to a basis for V, if and only if we have an eigenbasis. Okay. Now since T has only one eigenvalue, lambda equal to 2. Okay? So any eigenvector V of T must be in the kernel of T minus 2i. Okay? So they must be in the kernel of 2i. Because of that one. Okay? And this is saying that any eigenvector x equal to as a coordinate vector, the beacon of V of A must be in the kernel of A minus 2 by 2. Okay, so that its B coordinator must be an eigenvector of the matrix representation, as we discussed before, and any such eigenvector of A must be in the kernel of this matrix. And the kernel of this matrix, so we find this is 0, 1, 0, 0. Okay, so this matrix is 0, 1, 0, 0. And the kernel is just alpha times 1, 0, alpha in R. Okay? Okay, so now the kernel is one-dimensional. So you can see the kernel is one-dimensional. So since okay, is 1 and less than 2, we cannot find the two linearly independent eigenvectors associated with the eigenvalue 2. All right, so we can't. So we cannot find an eigenbasis, and so T has no. So T has no diagonal matrix representation. Okay. So now we have an example that is hopeless to find any diagonal matrix representation. The reason is because we can't find any eigenbasis. We can't. Okay? We can't find eigenbasis. So it means that we are short of eigenvectors. All right, now right, so now the coefficient, again, the third example, the coefficients are reals, right? And the A, you consider is 1, 2, minus 1, minus 1. Okay? So the eigenvalue of T are solutions of determinant T minus lambda I. So it's determinant of A minus lambda 2 by 2. And so this is the determinant of minus lambda 2 minus 1 minus 1 minus lambda. And this is lambda squared plus 1 equal to 0. So the eigenvalues are solutions of this polynomial. And the solution must be in R. Why? Because we are talking about a real case. Okay, our vector space are over the real numbers. Okay, so that the eigenvalue considered should be also in R. But this polynomial equation has no real solutions. Okay, so which is none, empty. Okay, so T has no real eigenvalues. Okay? And no eigenvectors. And no eigenvectors in V. Right? So that's T has no diagonal real matrix representation. Okay, so this case is because that we can't solve the polynomial equation because we restrict ourselves to the real case. So that the reason for X to T do not have any diagonal real matrix representation is because we don't have any real eigenvalues. So the reason is different from the previous example. In the previous example, we can solve the polynomial equations. Okay, but we are short of eigenvectors. Okay, Now the first example, now we consider complex case. Okay, and the metric representation is the same, 1, 2, minus 1, minus 1. Okay, so we have the same metric representation. Okay, and the eigenvalues of T are solutions in C of lambda square plus 1 equal to 0, which are I and minus I. So we have two eigenvalues, and both of them are complex, actually pure imaginary here. So we have eigenvalue I and eigenvalue minus I here. All right. Now an eigenvector of T associated with eigenvalue I is a non-zero vector, okay, in the kernel of, in what? In the kernel of T minus I. Okay. So suppose we have an eigenvector V, right? Okay. All right, and so we have to solve. So now V is in the kernel of T minus II. If its metric representation, its beta is B coordinate is in kernel in this kernel, and this is kernel of 1 minus I, 2 minus 1 minus 1 minus I. Okay, so we consider the complex matrix, and to solve its kernel, and we find that this is minus 1 minus I and 1 alpha in C. Okay. Okay, so take U with the B coordinate to be minus 1 minus I, 1. i.e. U becomes to minus 1 plus I, V1 plus V2. Okay, so this, which is an eigenvector of T associated with eigenvalue I. Okay, so similarly, V is in, we want to find eigenvectors associated with eigenvalue minus I. So we consider the kernel of T plus II. Okay, and again, So this matrix, after some algebraic manipulation, this becomes to the kernel of this complex matrix. All right, complex matrix here, and by solving by using the elementary row operation, okay, we find the solutions to be a multiple of this vector. Okay, so we take W with the B coordinate to be this one, minus 1 plus I, and 1. So i.e. the W is equal to minus 1 plus I, V1 plus V2, and which is an eigen vector of T associated with eigenvalue minus I. Okay, so for each eigenvalue we find an eigenvector. Okay, and so we collect them together. Okay, so we let C to be the set of U and the W. Okay, right, and we claim. So again, C is a basis for V. Okay, C is a basis for V. Well, it would be sufficient if we prove that C is a linearly independent set. Because if C is a linearly independent set, and because the size of C is 2, 2 is equal to the dimension of V. So this linearly independent set becomes to be a basis. Okay, so consider a linear relation again on C alpha U plus beta W equal to 0 vector. So this implies that, so we just do the substitution here as a linear combination of V1 and V2. Okay, V1 and V2 are vectors in the basis B there. Okay, basis B here. So we have minus 1 plus I. So we will do, we find that minus I alpha minus 1 minus I beta V1 plus alpha plus beta V2 equal to the 0 vector. Okay. Now, because V1 and V2 are vectors in basis B, and basis B is a linearly independent set, so that we have must be 0. So the coefficient must be 0. Okay. So we have two linear equations, and solving them, we find alpha and equal to beta equal to 0. So C is a linearly independent set of two vectors. Okay. Oops, maybe I will say size 2. And size 2 is equal to the dimension of V. So C is a basis for V. And because the vector in C are eigenvectors, so C is an eigenbasis for V. And so this is so that the metric representation of T with relative to this eigenbasis becomes to I. Okay, so it's which is diagonal. Okay, so we have a diagonal metric representation now. Okay, so in the complex case, we have the same metric representation as in the real case, but because we are considering the complex case, so we can solve the polynomial equations to find two solutions, I and minus I. Okay, and so we find the two complex eigenvalues, which is allowable, right, in the complex case. And then we can construct an eigenbasis so that the linear operator T can be diagonalized. Okay, and here is the diagonal metric representation. All right, the last example. The last example is here that scalar is complex, and the metric representation now is I, 1, 0, I. Okay, right, and so the eigenvalues. So the eigenvalues of T are solutions in C of the polynomial equation. So it's so this is lambda minus I square equal to 0. So now if we solve them, so the solution which are I. So we have repeated the solution. All right, so thus T has only one eigenvalue, lambda equal to I, with algebraic multiplicity 2. Okay. All right. So now, so any eigenvector of T must be in the kernel of T minus lambda I, right? So any eigenvector V. Okay. So this is saying that any eigenvector x equal to of A must be in the kernel of A minus I 2 by 2. Okay? And so the matrix A minus little I times capital I 2 by 2 becomes 0. This matrix, and this becomes 2, 1, 0. Okay. So it's all right. So the dimension is 1. So since the dimension of the kernel of is 1, which is less than 2. Okay. Once again, we cannot find two linearly independent eigenvectors associated with eigenvalue lambda equal to I. So the conclusion is that T has no diagonal matrix representation. Okay? So even we go to the complex case, we may encounter the situation that we are short of eigenvectors. Again, all right? So, so the shortage of eigenvectors will be the fundamental limitation, okay, for a linear operator to have diagonal matrix representation. Okay, so that is the limitation. Okay, and so these 5 examples demonstrate a lot of phenomena, so you can perceive. Okay, and we will solve the problem partially in this chapter. Okay. And we will give other partial solutions in chapter 8 later. Depends on how much time left for us to cover the material. Okay. Okay, so now the first theorem is a supplemental theorem. All right, so T, okay. So the information is that V, an n-dimensional vector space. Okay? And the T, V to V, a linear operator on V. Right. Then the determinant of T minus lambda I is a polynomial of degree n in lambda with leading coefficient minus 1 to the nth power. this polynomial is fundamental, important, because when we want to know the eigenvalues, we have to solve a polynomial equations. Okay. So now we have to characterize this polynomial. And then the theorem says that it's a polynomial of degree n if the vector space V is n-dimensional. And the leading coefficient is nth power of -1. Okay, so here is the proof. So let A to be the metric representation of T relative to a basis for V. Okay, then the determinant of T minus lambda I becomes to the determinant of A minus lambda I n times n. Okay, and so we will write down. This is A11 method. A12, A1n, A21, A22 minus lambda, A2n, AN1, AN2, ANN minus lambda. Okay, and so we will rename the entries of this matrix to be B11, B12 up to B1n, B21, B22 up to B2n, and the Bn1. The last row is Bn1, Bn2 up to Bnn. Okay, and where Bij is equal to Aij if I not equal to j. So if the entries is off diagonal, then Bij is equal to Aij. But if on the diagonal, Bii would be equal to Aii lambda j when I equal to j. Okay, so we have this one. Now we have so we can use the expansion formula we developed in chapter 4. So for every permutation in the symmetry in the set of Sn, the sign of the permutation, and this is B1 sigma 1, B2 sigma 2, and the Bn sigma n. Okay, so this is our expansion formula. Okay, and so you can see that so this is the sum of n factorial terms, right? Each term is a sign, so sign is just -1 plus 1, right? Okay, and put there. Okay, so by the expansion formula for determinants, which is in the theorem 4.2.d. Okay, I show that for you in chapter 4. Okay, so we have the theorem here. Now, you see this polynomial becomes to the sum of many polynomials, right? Each product corresponding to one polynomial in lambda. So we have n factorial polynomials to add together, right? See that? All right, so now we look at a particular term here. For sigma with sigma I equal to I. So if the permutation is the identity permutation, okay? So there is only one, I think I have to say, there is only one sigma such that sigma I equal to I for all I from 1 to n. Okay? Which corresponds to a term sine sigma times B1 sigma 1, B2 sigma 2, Bn sigma n. This is equal to, and because that is 1, 1, 1, 1, 1, so that the sign is 1. So this is 1, because this is the identity corresponding to the identity matrix. So the determinant of the identity matrix is 1. Okay, and we have B, 1, 1, B2, 2, Bn, n. So what is that? So this is A11 minus lambda, A22 minus lambda, up to Ann minus lambda. And this is minus 1 n factorial. Okay? Right? So which is a polynomial of degree n with leading coefficient minus 1 to n's power. Okay, so this term is the polynomial of degree n with leading coefficients n's power of minus 1. Is that okay? Because that is a product of linear factors. Each factor is degree 1. Right? Now any other term, sigma, such that sigma I not equal to I for some I in between 1 and n. So any other sigma, right, such that they must have sigma I not equal to I, because if every sigma I equal to I, then this term, right? So the other permutation should have sigma I not equal to I for some I. Okay. Then B I sigma I becomes to A I sigma I. It's a constant. And the corresponding term is the sine of sigma b1 sigma 1, b2 sigma 2 up to bn sigma n, right? This one is a polynomial of degree less than or equal to n minus 1. Why? Because that the b1 sigma 1, every bi, either constant or a linear vector. But we already know that there is some I such that the bi sigma I is a constant A. So at the most we have n minus 1 linear vectors here, right? So this term is a polynomial of degree less than or equal to n minus 1. Okay? So now we go back to here. In n factorial terms, there is one term of degree and the other terms are polynomials of degree less than or equal to n minus 1. So the conclusion is that the determinant of t minus lambda I is sum. It's a polynomial of degree n with leading coefficient. Nth power of n minus 1. And we have done. Questions? Right now, the determinant of t minus lambda I will be called the characteristic polynomial of T. And the equation equal to 0 is called, is called the characteristic equation of T. So, eigenvalues of T are solutions in F. In F depends on the scale field, either real or complex, right? Solution of the characteristic equation of T. Questions? All right. Now, so let alpha be an eigenvalue of T. So we know alpha is just a solution of the characteristic equation, right? So let alpha be an eigenvalue of T if lambda minus alpha to the raised to the nth power divide the characteristic polynomial right? Suppose that because when we want to solve the characteristic equation, we have to split, right? To split the characteristic polynomial into linear factors. Right? Solving characteristic equation is equivalent to splitting the characteristic polynomial into linear factors, as we have done in the 5 examples we mentioned before. So if we have the nth power of the linear factor, right? This is a factor of the characteristic polynomial. But if we want to raise one more, but this is not. Okay. Then the M is called the algebraic multiplicity. Okay, of eigenvalue alpha. So the algebraic multiplicity of eigenvalue must be greater than or equal to 1, at least 1, because it is it's a solution of the characteristic equation. Okay, so that but the multiplicity of an eigenvalue may be more than 1. As our example, we have eigenvalue with multiplicity 2, right, for them. And if n is big, the n-dimensional, if n is big, you may have eigenvalue with large multiplicity is possible. Okay, for example, if n is 1,000, then you may have an eigenvalue which is 100. Okay. Okay. Oh, right. So let's take a break. To save time, please take break for 5 minutes only. Okay. Okay, so all right. So now the first theorem 6.1.8, characterized the characteristic polynomial. Right? We know the characteristic polynomial has degree n, and the leading coefficient is the nth power of -1. The second thing is that once we solve the characteristic equation to find the eigenvalue, then for each eigenvalue we have to find eigenvectors, especially independent eigenvectors, right? Because we want to find more linearly independent eigenvectors as many as possible. So we have to solve the kernels. Okay. Now, so we have to deal with this problem now. So in general, for a scalar alpha, we define E alpha to be the set of all vectors which satisfy the eigen equation, but with alpha fixed. And as you know, if alpha is not eigenvalue, then we will not have any eigenvector, right? Otherwise, it is an eigenvalue already, right? So alpha is arbitrary scalars, and so E alpha to be the set. Okay, so which is the solution? Which the solution set of eigen equation TV equal to alpha V. But here, alpha is known. Okay, so alpha is known. We already know that, and we'll try to solve it. But this is now it is clear that E alpha is the kernel of T minus alpha I. Okay, so it is clear that because that so this is equal to V such as zero vector. Okay, right? So this is equal to the kernel of so E alpha just is the kernel of this linear operator. Okay. So lemma 6.8 for each scalar alpha, E alpha is a subspace of V. Okay, I think I don't need to give a proof. The proof given there, I think, is redundant because that is a kernel, and we proved kernel is a subspace already. Okay, so that, but anyway, I already put there. Okay, you can ignore the proof. Now, if alpha is an eigenvalue of T, then the the E alpha, okay, is non-trivial. Means that by theorem 6.1.1, okay. Okay, so this non-trivial means that it contains at least one non-zero solution. Okay, and we know any non-zero vector in E alpha is an eigenvector of T associated with eigenvalue alpha. Okay? For this reason, E alpha is called the eigenspace, okay, of T associated with eigenvalue alpha. Right? And the dimension of E alpha is called the geometric multiplicity of eigenvalue alpha. Okay. So geometric multiplicity means that the maximum number of independent eigenvectors we can find associated with the same eigenvalue alpha. So if the dimension of the eigenspace E alpha is 1, then we can only find one vector to form a linearly independent set. But if the dimension of E alpha is k, then we can find k eigenvectors from the eigenspace, and these k eigenvectors form a linearly independent set. Okay, and that is crucial for us. Okay, crucial for us to determine whether we are short of the eigenvector or not later on. So geometric multiplicity directly related to the diagonalization of linear operator. Okay, so it's a very important concept, geometric multiplicity. Okay, algebraic multiplicity is easy. You just vectorize this characteristic polynomial. You vectorize them. Okay, and especially in the complex numbers, in the complex number field, by the fundamental theorem of algebra, every polynomial with complex coefficient can be factorized into linear vectors. This theorem has been proved by Gauss. Okay. So, and I think that would be in Appendix B, right? The Appendix B mentioned the fundamental theorem of algebra. So that at least in the complex number field, that polynomial, characteristic polynomial, can be factorized into linear vectors. So once you factorize the characteristic polynomial into linear vectors, then you know the algebraic multiplicity for every eigenvalue. Okay? So this is purely algebraic because you just factorize them. Okay. not related to diagonalization, all right, of a linear operator anyway. But when we resolve to the question whether we have a diagonal representation of a linear operator, then we have to look at the geometric multiplicity of every eigenvalue here. Okay, and you have to find first the eigenspace first and to determine its dimension. Okay, and of course that we know the dimension of the eigenspace will be at least 1. Okay. Okay, so now I will prove an important theorem. Theorem 6.1.2. The geometric multiplicity of an eigenvalue alpha of a linear operator T on an n-dimensional vector space V over F. So F can be R or C is no greater than the algebraic multiplicity of that eigenvalue alpha. So geometric multiplicity will be less than or equal to the algebraic multiplicity. Okay, so that is the statement of theorem 6.1.2. Okay. All right. The theorem has been stated in the textbook without a proof, but we are able to prove it now, okay? Because we have enough knowledge to give a proof. All right, so let P be P is the dimension of E alpha, okay? Right? So that, okay, and let V1, V2 up to Vp be a basis for V. For E, sorry, E alpha. Okay. Okay. So this is the information. So suppose that E alpha, P is the dimension of E alpha, and we have a basis. Okay. Of course, each Vi is an eigenvector of T associated with eigenvalue alpha. Okay, of course that. Now, if P equal to n, then E alpha is just equal to V, and this set okay, it's an eigen basis. It's a basis, not nice. We just need a base. It's a basis. It's already a basis for V already. Okay, so if P is less than n, so we extend the set okay to a basis B. So that is V1, V2 up to Vp, and Vp plus 1, that Vn for V. And this can be done by theorem 5.2.16, right? So we show that in chapter 5. So we can extend this linearly independent set into a basis for V. Okay? So this is for V. Now we look at the image of vectors in the basis B. So now TV1, what is TV1? TV1 is alpha V1, okay? Because VI's for I from 1 to P are eigenvectors of T associated with eigenvalue alpha. So TV1 is alpha V1, right? And so that to find its coordinator, to find its B coordinator, right? So that we have alpha V1 plus 0, V2 plus plus 0, Vp plus 0, Vp plus 1, plus plus 0 Vn, okay. TV2, V2 is also equal to alpha V2. So it's 0 V1 plus alpha V2 plus plus 0 Vp plus 0 Vp plus 1 plus plus 0 Vn up to T Vp, it's alpha Vp, okay? And this is 0 V1 plus 0 V2 plus plus alpha Vp plus 0 Vp plus 1 plus 0 Vn. Okay, so we just look at the image of the first P vectors. All right, from that, then the matrix representation. Then now I will look at the matrix representation. Okay, so now the matrix representation of linear operator T relative to this basis B will be T V1 B T V2 T Vp T Vp plus 1 T Vn. Okay, so that is the matrix representation. And the column we find this is alpha, 0, 0, and also 0, 0. You can see alpha 0, 0, 0, 0, 0. And the second column was 0 alpha, 0, and 0, 0. And go to alpha. And this is all zeros. Okay? But for the rest, from VP1 can be arbitrary. All right? So this part will be called D. And this is C. Okay? And the D here is P times n minus P. And this is the n minus P times n minus P. Okay. Okay? So this is the, and this is the upper triangular block matrix, because this is all zeros. Okay? Now, the characteristic polynomial of T is, we call F lambda. So this is the determinant of okay, so we find that. And this is actually the determinant of, all right, lambda I. So this is actually alpha minus lambda, the identity matrix. They have two parts. And we have a zero matrix, n minus P times P. And we have D, P times n minus P. And we have C, C minus lambda identity. Okay, so we have this one. So the difference, right, becomes to, again, it's upper triangular block. It's a block upper triangle matrix here. Okay. So that the determinant we know, right? So this is the determinant of alpha minus lambda, identity P times P, times the determinant of the rest here is C minus lambda I, n minus P times n minus P. Okay? So this is by theorem 4.2.E. We know how to compute the determinants of triangular block matrices. Right? And we call this, so this is alpha lambda, alpha times minus lambda piece power. This is piece power. And this one we call the G lambda here. Okay, this is a polynomial we call G lambda. Questions? So the crucial point is we know how to compute the determinant of this upper triangular block matrix. Okay, and so therefore, lambda minus alpha piece power divide the characteristic polynomial. So this implies that P is less than or equal to the algebraic multiplicity of alpha. Okay? Because you may have more factors than P of the lambda minus alpha. You may have more. But at least we know this factor is the piece power of lambda minus alpha is the divisor of f lambda. So that P is less than or equal to the algebraic multiplicity. But what is P? P is our geometric multiplicity of alpha already. Okay? So we have done. So for every eigenvalue alpha, its algebraic multiplicity will be less than or equal to its algebraic multiplicity. Okay? So that's the case. Okay? And then later on, we will see a theorem, a supplemental theorem that that a sufficient and necessary condition for a linear operator T to have a diagonal representation, if and only if this inequality becomes to equality for every eigenvalue. Okay. And also equal to n. One more. I will state that precisely later. All right. So T. Okay. Another subject is that in our examples, every time when I pick up an eigenvector from associated with an eigenvalue. Okay. So different for different eigenvalue, we pick up different eigenvectors. And every time I have to show that if I collect them together, I have to show that they form a linearly independent set, right? Every time I have to show that. But this actually is a factor. So I have to show. This is a general statement. So suppose that T is a linear operator on a vector space V. And this vector space V not necessarily finite dimensional, just arbitrary vector space. Now if U1, U2 up to UK are eigenvectors of T corresponding to distinct, all right, corresponding to distinct eigenvalues, lambda 1, lambda 2 up to lambda k, respectively. Then U1, U2 up to UK, they form a linearly independent set. Okay, so this is a general theorem. It's crucial that these eigenvalues are distinct. Okay, they are distinct. All right. So So we use proof by contradiction. So suppose that U1, U2 up to UK is linearly dependent. Okay, it's linearly dependent. Now, since U1 is an eigenvector of T, it is non-zero, so that the singleton is a linearly independent set. All right, so U1 itself is a linearly independent set. Now we try to enlarge the linearly independent set one by one. Okay, U1, U2, U3. All right, and so we let J be the largest index in 1 to K, such that U1, U2 up to Uj is a linearly independent set. Okay? Right, so we enlarge, because this singleton is linearly independent. And then we see, how about include U2? Does it linearly independent? Yes, then we move on. Up to the biggest J, okay, this is linearly independent. And then if we consider U sub J plus 1, then when we add U sub J plus 1, then this set becomes to linearly dependent, then we stop. Okay, so J is the largest index, which is linearly independent. All right, then J must be less than K, right? Otherwise, U1, U2 up to UK is linearly independent. A contradiction, and which is a contradiction to this assumption. Okay, so which is a contradiction. Okay, right, so that's U J plus 1, right, is a linear combination, right, of U1 up to Uj, i.e. U J plus 1 is equal to alpha 1 U1 plus alpha 2 U2 plus alpha J Uj. For some scalars, alpha 1, alpha 2 up to alpha j, not all zeros. Why? Because if all the coefficients are zeros, then U sub j plus 1 is zero vector, which is impossible. Why? Because U sub j plus 1 is an eigenvector. So any eigenvector cannot be zero vector, okay? So that the scalars, not all zero. All right? Now we apply linear operator T on both sides. So now T uj plus 1 will equal to t so this is alpha 1 t u1 plus alpha j t uj, but and so that this is alpha 1 lambda 1 u1 plus alpha 2 lambda 2 u2 plus plus alpha j lambda j uj. Okay, because the ui's are eigenvectors corresponding to eigenvalue lambda I. We have that. Okay, so this is, say, this is 1 and this is 2. Now, if we multiply, and here this is the lambda j plus 1 u j plus 1. Sorry. So this lambda, this one, okay. Implies that. Okay. So we have, because t of uj plus 1 is lambda j plus 1 and uj plus 1. Yeah. Now if 1 multiply with lambda j plus 1, so if the first is multiplied with lambda, we have a lambda j plus 1 uj plus 1 equal to alpha 1 lambda j plus 1 u1 plus alpha 2 lambda j plus 1 u2 plus plus alpha j lambda j plus 1 uj. So this is the third equation. Okay, so now we take the difference. So the third equation minus the second equation give us 0. All right, so because they cancel each other, right? And here we have an alpha 1 and the lambda j plus 1 minus lambda 1 u1 plus alpha 2 and lambda j plus 1 minus lambda 2 u2 plus plus lambda j plus 1 lambda j uj. So we have this one. So this is 0 vectors. All right. But as we know, u1, u2, uj is a linearly independent set. And this is a linear relation on this linearly independent set, right? This is the linear relation on this. So that all the coefficients must be 0. Okay, this implies that alpha 1 lambda j plus 1 minus lambda 1 is 0. Alpha 2 lambda j minus 2 is 0. Alpha j lambda j plus 1 minus lambda j, yeah, things u1, u2 up to uj is linearly independent by our construction, right? Because this is our linearly independent set. Now, but eigenvalues are distinct. So they are non-zero. So this means that alpha 1 equal to alpha 2 equal to alpha j, all 0. So the coefficients are all zeros. Well, but here the coefficient cannot be all zeros. So we have a contradiction. Okay, so we have a contradiction. And then we have no way to go. So if we suppose that the set is linearly dependent, we find that we will reach a contradiction eventually. Okay, so that U1, U2, UK is a linearly independent set. Okay, the end of proof here. Okay, so a corollary is that so if T is a linear operator on an n-dimensional vector space, right? Suppose we have n-dimensional vector space. If T has n distinct eigenvalues, so if you split the characteristic polynomial and find that they can be split into n different linear vectors, then it has n distinct eigenvalues. So if T has n distinct eigenvalues, then T has a diagonal matrix representation. Okay, so that is easy to prove. So let number 1, number 2, up to number n be distinct eigenvalue of T, and let Ui be an eigenvector of T associated with eigenvalue lambda I. Okay, because lambda I is an eigenvalue, so it has at least one eigenvector. So now by theorem 6.1.3, the collection of these n eigenvectors, right, is a linearly independent set. Okay, and then a basis for V. Why? Because the size of the linear independent set is n. So this is by theorem 5.2.10. Okay, so 5.2.10 tells us that this linearly independent set is a basis, and because it consists of eigenvectors, so it's an eigenbasis, and so that okay, and we call this set as B. Okay, so that right. So this matrix representation, it's TU is lambda 1, U1, B, lambda 2, U2, lambda n, UN. Okay, And this is lambda 1, 0, lambda 2, 0. So it's a diagonal, which is diagonal. Okay, we have done. So this is a sufficient condition. So corollary 6.1.1 provides us a sufficient condition that a linear operator have a diagonal matrix representation. Okay, and this is a very easy sufficient condition. Now, I give the last theorem. Okay. It gives the sufficient, and then, so this is a sufficient condition. I'll give you the necessary sufficient condition, right? So T, a linear operator on an n-dimensional vector space V. So it's n-dimensional. All right, and then let lambda 1, lambda 2, up to lambda k be all distinct eigenvalues of T. And of course, the number of distinct eigenvalues can be from 1 to n. Oh, maybe 0. Okay, if 0, then you have nothing to say. Okay, so just say we have at least 1. Okay, and we let mi tilde to be the dimension of the eigenspace of lambda I. Okay, so this one be the algebraic multiplicity. Geometric, I'm sorry. So this is the geometric multiplicity of eigenvalue lambda I for I from 1 to k. All right, so then T has a diagonal matrix representation right? So T has a diagonal matrix representation if and only if M1 tilde plus M2 tilde plus MK tilde is equal to N and is equal to the dimension of V. So that means that you are able to find enough eigenvectors from each eigenspace. Okay? And so that the total number, you add them together, the total number of the eigenvectors will be equal to the dimension of N. And then you have done. Okay, so this is the if and only if condition. Necessary and sufficient condition we'll have. All right, so the proof forward direction. Suppose T has, so we let suppose that T has a matrix representation which is diagonal relative to a basis B. All right, so we write down, and because we have only K, so that it's possible that Okay, so we put them. All right, so this is, so we put the eigenvalue here. This is diagonal is 2 and k, and the k here. Right, and they are all zeros. And here we have m1, we have m2, and here we have mk. Without tilde, they are called algebraic multiplicity. So they are, so these are algebraic multiplicity. Okay, so M1 is the algebraic multiplicity of number 1, M2 is the algebraic multiplicity of number 2, etc. Okay, so this is the a diagrammatic representation like this one. Okay. And where B, so I will give a name V11 up to V1M1 and V21 up to V2M2. Okay, so we have and that's the VK1 up to VKM sub K. Is an eigenbasis for V. Okay, and we know that M1 plus M2 plus plus Mk equal to n equal to dimension of V. Right. So this is the data, the given condition. When a linear operator T has a diagonal metric representation relative to a basis B, and we know we have only k distinct eigenvalues, so that you can see that this diagonal matrix should be can be arranged in this way. So number 1, number 2, etc. Number k, right? And the size of each block here, this is M1, so corresponding to the algebraic multiplicity of the corresponding eigenvalues there. And because this is n times n, so we know M1 plus M2 plus Mk is n. Okay, this is all the information we can have because of to have diagonal metric representation. Questions? Any questions? So this is given. I just express the given information explicitly. All right, so this is all the data you know. Now, So now we know, because that beta B is eigenbasis, so we know that TV11 is lambda 1 V11, TV1M1 up to TV is lambda 1 V1M1. Okay, and for TV21 is lambda 2 V21 up to TV2M2 is equal to lambda 2 V2M2, and the TV, because the column vector, so that we know TVK1 is equal to lambda K VK1, that TVKMK is equal to lambda K VKMK. Okay, so from this metric, because they're diagonal, so we have that. Okay, so this is the first column. The first column corresponding to this eigen equation, and second column, etc., up to the M1's column. They are all corresponding to eigen equations, and this the scalar here is the eigenvalue number 1. Okay, so this is from there, so that we collect them. So V11 up to V1M1 together. So this M1 vector, eigenvector, put together, because they are all eigenvectors corresponding to eigenvalue number 1. And we collect eigenvectors corresponding to eigenvalue number 2 together. And the last one is eigenvectors corresponding to eigenvalue number k. Okay, so they are linearly independent sets in eigenspace. In eigenspaces, this E lambda 1, E lambda 2 up to E lambda k, respectively. Because the big set is linearly independent, so the smaller set, every small set is also linearly independent. Okay, so this is a linearly independent set in the eigenspace E lambda 1. This is a linearly independent set of the eigenspace E number 2, etc. And so that the dimension, so M1, okay, is less than the dimension of E lambda 1, and the M2 is less than or equal to the dimension of E lambda 2, etc. up to Mk is less than or equal to the dimension of E lambda k. Okay, so we have that. By what? By theorem 5.2.12. Okay, so if a vector space, a finite dimensional vector space, has a linear independent set of size k, then the dimension, either the vector space is infinite dimensional, or if it's finite dimensional, then the dimension will be greater than or equal to k. Okay, so we have that. But what is that? But this is M1 tilde. This is M1 tilde. This is M2 tilde. Okay, so that we have Mi. So we have Mi less than or equal to the Mi tilde for all I from 1 to k. Right? But we know the algebraic multiplicity will be less than the geometric multiplicity will be less than or equal to the algebraic multiplicity by theorem 6.1.2, we just proved there. So that Mi tilde must be equal to the Mi, all right, for all I equal to k. So this implies that, but M1 plus M2 equal to n, so this says that M1 tilde plus M2 tilde plus plus Mk tilde is equal to n, equal to the dimension of V. Okay, so we have done the first part. So if T is diagonal, has a diagonal metric representation, then the sum of all the geometric multiplicity, all right, of all eigenvalues is equal to n, the dimension of V. Okay, so we we establish this direction. Okay? Right? So the only part is the reverse side. The reverse direction. All right, so okay. By the way, any question about the proof of the forward direction? There? No? Okay. Very good. All right. Now, okay, so we let B1 to be V11 up to V1 M1 tilde. Okay. And the B2 is V21 up to V2 M2 tilde up to BK to be V1 VK1 up to VK MK tilde. Okay. So we let them be basis for eigen spaces E lambda 1, E lambda 2 up to E lambda k respectively. Okay, respectively. Okay, so because the dimension of E lambda 1 is M1 tilde, dimension of E lambda 2 is M2 tilde, etc. Okay, so we suppose. And then we take the union. Okay, we take the union. So that is V11 up to V1 M1 tilde, V21 up to V2 M2 tilde, VK1 up to VK MK tilde. Okay, and the size of this set is n, is the dimension of V. Why? Because this is our assumption, right? We assume that the sum is equal to n. Yeah. Right. So this. So you have this one. They have no the intersection of all the bases will be empty set. The reason is very clear. If a vector cannot be an eigenvector of lambda 1 and also eigenvector of lambda 2, cannot. It's impossible, right? So they must be disjoint. B1, B2, and BK, they are all disjoint, of course. And so when we take the union, they are disjoint union. So sometimes I put that here, means that they are disjoint union. Okay? And so the size is n. All right? So the only left thing is to, so that, and now I want to prove that B set is a linearly independent set. Okay? Okay, so consider a linear relation on the B set. Okay, so we have A11, V11 plus A1 M1 tilde, V1 M1 tilde plus A21, V21 plus A2 M2 tilde, V2 M2 tilde plus plus A K1 V K1 plus A K mk tilde vk. All right, suppose we have a linear relation like this one. And I already group some sum together, so we have k groups here. All right, so we have k groups. And so this is in, so that this is in E lambda 1. This is in E lambda 2. And this is in E lambda k. Okay? So each group is in different eigenspaces. Okay, so they are different. Right? If any of them non-zeros, then if this is non-zero, then this one must be an eigenvector. Right? So this is an eigenvector. If this is non-zero, then this must be an eigenvector associated with number 1. If this is non-zero, then this must be an eigenvector associated with number 2, etc. Now, but we just prove eigenvectors corresponding to distinct eigenvalues form a linearly independent set. Right? But this is a linear relation with non-zero coefficient here. This is impossible. So if any parentheses contain non-zero vectors, then you get a contradiction. Is that clear? So this implies I1 V I1 plus plus I mi tilde V I mi tilde equal to 0 vector for all I in 1 to m. Okay. This implies that. Otherwise, okay, by theorem, distinct 6.1.3. Okay, so by theorem 6.1.3. So each parenthesis, each group together must be 0 vector. Because if there is any of them to be non-zero, then the vector, this linear combination, becomes to an eigenvector corresponding to eigenvalue lambda 1, anyone. And so you will have a non-trivial linear relation. Why? Because the coefficient is 1. All the coefficient is 1. So whenever you have a group in the parentheses to be non-zero, then you get contradiction. So every group should be 0. No exception. Okay? So this is from theorem 6.1.3. Okay. All right, and this shows, but each B is a linear independent set. So this implies that AI1 equal to AI2 equal to AI mi tilde equal to 0 for all. Okay. So this implies that B is linearly independent. Okay, so B is linearly independent, and it's an eigenbasis for V. Since E equal to the dimension of V equal to n. Okay, and so it's diagonal. And we have done. Okay, to the end of proof. So once we find an eigenbasis, then relative to this eigenbasis, the metric representation is diagonal. And we have done. That's it. Okay, so this is the final theorem I gave to you. And that's the end of chapter 6. Right? Okay, so we will have midterm, second midterm next Wednesday, coverage X, chapter 4, 5, and 6. Okay. All right, so good luck. And see you next week.